Hello and welcome back to Calculus2. We are continuing our section 10.4 on Divergence Test, also known as N-term test, Integral test, and P-series. Last time we talked about the Divergence Test. We said Divergence Test can only spot divergence. We said if the limit of the sequence inside the series, if that limit is anything but zero, series immediately diverges. So if the limit is 1, if the limit is 10, if the limit is negative 5, infinity, whatever. So if it's different than 0, series would diverge. And at the end, I asked about, and I labeled it as the evil one because you make a lot of mistakes with this one, so hopefully we'll fix it with integral test. We said that this one is inconclusive, and it's inconclusive because the limit is 0, and if the limit is 0, we don't know, right? Now we are going to use integral test to solve this. But before we get the integral test, we have to know the procedure for integral test. So let's go and write down the procedure for integral test. So when you have a series that goes to infinity, it doesn't matter where it starts. Remember that we only said the only one that matters where it starts is geometric, right? The other ones can start anywhere. So we have the series of some kind of an, right? And you want to make sure, we want to check whether it converges or diverges. So this is what we do. We take this sequence an and we write it as f of x by swapping n with x. I'm just going to give an example and delete it because I don't want this example to be the part of definition. I will need all of this space to write the procedure for integral test. So what I'm writing now in black is not supposed to be there. I'm just explaining what I mean by this. What I mean by this is that if you have an to be, let's say, 3n plus 1, then this one over here will be 3x plus 1. So that's what I mean. You will transform your sequence into a continuous function. You know that the one on the left is discrete, dot, 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 right? And the one on the right is a continuous line. So we are transforming the discrete world back into continuous world that you are all used to. So that's the first step. And now we say if f of x is, number 1, continuous on some interval. You know what? Let's put value m over here. So this will be now m to infinity. So now m to infinity. So if f of x is continuous, positive, decreasing, on m to infinity. Actually, I'm going to do this. There we go. So if it's continuous, positive, and decreasing on this interval m to infinity, then summation m to infinity an and the integral m to infinity f of x dx both converge together or diverge together. That's it. Now, this is a 5-part problem. Part number one is to understand your domain, which is m to infinity, and transfer discrete into continuous. Part number two is to prove that it's continuous. Part number three is to force positive. Part number four is to do decreasing. And then part number five is to solve the integral, if all of these pass. Once you solve the integral, this is type 1, right? It's a type 1 improper integral. And we know that type 1 improper integrals either converge or diverge, right? So if the type 1 converges, then that means that the series converges as well, which is why they say both converge together. So once you do the transformation, if all three of these pass, then these two will do the same thing. Both diverge. So we are actually taking a step away from our discrete world, and we are taking continuous functions f of x, and we'll use improper integrals. Now, for improper integrals, what do you guys have? Well, obviously you have your limit b goes to, so you're not going to escape the limit again, right? I promised every section to have limits. Obviously, you can't escape it. So we are now going to do these problems. They tend to be long. So we are going to, remember, grab the wrist, right? And then we have the wide circles, then the other side, right? Then you can do this, thumb down, and then grab it up here. Apply pressure on the top to stretch all of these. Great. So now we can have our 30 minutes problems in peace. Should be a page per problem. Sometimes it's going to bleed to the second page. It depends on how complicated the three proofs get to be. Now we're going to start with the harmonic series 1 over n. That is the one that we couldn't solve with our divergence test, right? So we're going to examine, let's say, 1 to infinity of 1 over n. You can start at 30 if you want, I don't care. You can't start at 0 because 1 over 0, right? But you can start at 1, you can go 2, 3, 4, you can start anywhere else. You are not allowed to start at 0 in this case. Cool. So what's my an? Well, it's 1 over n, right? That's the sequence that it's within the series. It's not going to be for the last time, but for the 100th time right now. This is a sequence, list of numbers with commas. When you add those, you get a series. So series on the left, sequence on the right, sequence is within the series. We say summation of an, summation of a sequence. Good. So what's my f of x? And what's my domain? Yes, 1 to infinity. Perfect. Bracket 1 to infinity. So that first value, if it starts at 2, it's 2 to infinity. If it starts at 30, 30 to infinity. And that value is included, right? So we have a bracket. Awesome. So first part of the problem is done. Extracting the sequence, converting the sequence into a continuous f of x function, and looking at the domain. Now we go into the three proofs. The three proofs are usually paragraphs or calculations, depending on what type of function we have. Now in this case, this is a very basic, cheap function. We can just look at the graph and be done. But for the most part, you will not be able to graph unless you spend another 40 minutes. Remember those problems from Calc 1? Graphing by hand? That 13 calculations you do, and then 40 minutes later you have a graph. Well, you do not really want to insert that here, so we'll do the proofs the other way. Do these proofs have to be done? Yes, because if one of the three fails, then integral test doesn't apply, doesn't hold, so you have to do something else. So you have to make sure, absolutely sure, right, to make sure that this stuff, all of these proofs have correct conclusions, right? And if they're all pass, then you get to do the improper integral. So the first question is the function 1 over x continuous on the domain 1 to infinity? Yes, because we know that the discontinuity for 1 over x happens at x equals 0. That's where the vertical asymptote is. But we don't care, right? Because our domain starts at 1 and we are going to infinity. So we only care about this part of the graph, red part of the graph, going to infinity, and that is continuous everywhere, right? So, yes, because x equals 0 does not belong to 1 to infinity. So this function is discontinuous, but the part we care about is continuous, so continuity pass. I will put the green check mark on it. Next one is, you can do this in any order. Let's say you want to do the positive next. So is it positive? Positive means has to be above x-axis, right? So all of the y values need to be positive values. Well, we see, yes, graph is above x-axis on 1 to infinity. Awesome. So pass that. And then the last part here is it decreasing? And that's also yes, because we see that it drops down. The graph, right, is clearly going to 0. But there are cute ways that you can do this, right? You can take a look at the first derivative. If the first derivative is negative, function is decreasing. We learned that in Calc 1. So yes, and we can just say f prime of x is negative 1 over x squared, and that's always less than 0 because you always have a positive number in denominator, right? For any value you plug in, when you square it, you get positive. Negative 1 is negative. Negative divided by positive is positive. So first derivative being less than 0 implies decreasing function. So we just proved, now this is just the simplest possible situation you can have with least amount of work. So we just proved all 3 conditions, and because all 3 conditions hold, I can go and take the integral of 1 to infinity of 1 over x dx. So that's my calculation that I have to focus on, right? So what do? Well, we first go with a limit. B goes to infinity, and you have your integral 1 to b. And then you have your dx over x. What's the integral of dx over x? Log x. Excellent. So we have our ln x computed from 1 to b. And now we have our limit. B goes to infinity of ln of b minus ln of 1, which is 0. And we have infinity, which is divergent. Time to answer the question. Does anyone care about your integral? No. Does anyone care about the proofs? No. What is the answer to the question? The answer to the question is what is happening with the series. And the series says if all 3 conditions hold, then these 2 here have the same fate, which is, in this case, divergent, right? They end up divergent together or convergent together. Well, since the integral diverged, here is what you need to write as your answer. Answer. Since, you can say, since all 3 conditions hold, and the integral 1 to infinity dx over x diverges, the series summation 1 to infinity 1 over n diverges by integral test. This is your answer. Everything prior to this box is partial credit, right? The question is asking you about divergence of your series, and you are clearly establishing that right here. So since all three conditions hold and the integral is divergent by the theorem that we learned earlier, the test, right? We know that series diverges, and that's what we care about. So this was our integral test where we showed what we couldn't detect earlier, and now we know harmonic series summation 1 over n from 1 to infinity or whatever to infinity diverges. That's what we know. Now we're going to have alternating harmonic series eventually, and we're going to have those series pop up in comparison tests and so on. So it's much better if you know the blue off the top of your head rather than computing the integral test for it every time you need it, right? Next example is what's happening with a series 1 to infinity of 1 over n squared. That's the next one, right? All right, so we have our an, which is 1 over n squared. Come up with f of x with 1 over x squared, and then have our domain 1 to infinity. So we have those. Then we draw the graph because we're lazy. This is one of those graphs that you can easily memorize, because when you square 1 over x, the negative branch will just pop up. You know, it used to be here. When you square all of those numbers, they become positive numbers. So they just jump the ship, right? They go up. And again, we are going from 1 to infinity. So we already see the same features as before. Is it continuous? Yes. On, right, 1 to infinity. Is it decreasing? Yes. Is it positive? Yes. So we have all of these pass, and we don't have to do a lot of work. Again, this is a basic function that you might know graph for. So can you do the continuity thing? Of course, you can do the proof by stating polynomials are continuous, and then the division, the quotient of continuous function is continuous as long as denominator is not 0. Denominator cannot be 0 because we are starting at 1, and there is your proof, right? Well, we'll do those detailed proofs for the spicier examples. This one is not a big deal. So now, since all three conditions passed, I can do the integral 1 to infinity of 1 over x squared dx, which is the limit b goes to infinity, integral 1 to b of x to the negative 2 dx, limit b goes to infinity, and then x to the negative 1 over negative 1 from 1 to b. And now I have limit b goes to infinity. I have negative 1 over b plus 1. And when I plug in infinity, this will go to 0 because I'm dividing a constant with infinity. So this works out to be 1. Works out to be convergent. That's the most important part, right? So when I integrate everything in here, I will get that the integral converges. And this is where we write the answer to the question. since all three conditions hold and integral 1 to infinity dx over x squared converges, the series summation 1 over n squared 1 to infinity converges by integral test. And this is the box that you take to the bank, okay, and cash in 4 points. Say 10 on the exam, right? Yes?
Will there be questions that ask if it does converge to
Hell no, even before you ask the question. And that is amazing thing that you're bringing it up, because generally people don't remember to ask that or don't ask that, but this answer here has nothing to do with the sum of the series.
Okay.
So integral converges to 1, we don't know what the series converges to. And this is a good time to go back to this piece of paper, guys, that I gave you. We're going to look at the rows 2 and 3, geometric and telescoping, go all the way to comments, and realize that the only 2 out of these 10, the only 2 we know summation for are geometric and telescoping. For the other 8, we will know whether they converge or diverge, and if they converge, we have no clue where they converge to. So the only sums that we will know are geometric and telescoping. The rest are all, we don't know. So we cannot claim here that this series converges to 1 because it doesn't, right? Now we can always ask computer science majors to add a couple of 1,100 terms, right? And give us a good approximation to where this might converge to, but that's technically what it is. Great. So we did 1 over n squared. Naturally, the next one is 1 over n cubed. We're going to go up to 16, and then we're going to stop. So 1 to infinity. We have our n to the n cubed. We have our f of x to be 1 over x cubed. And our domain to be 1 to infinity. And then we have to do those 3 proofs. So is it continuous? So I'm going to do the 3 dots here. I'm going to say work goes here. And then I'm going to jump to the answer and write, since all 3 conditions hold and integral 1 to infinity dx over x cubed converges, the series summation 1 to infinity 1 over n cubed converges by the integral test. Now you're going to say, I don't believe you. Fine, go home and compute it. You have all the steps. I just needed the n cubed result. N to the 4th also converges. N to the 5 also converges. 1 over n to the 6 also converges. And this pattern that we just developed here using integral test, and then there is a proof that the honors students, the honors calculus courses can have fun with. What we did here is we developed something that is called P-series, which is test number 5 that we are learning in this class. Marks the half of your tests, guys. P-series. And it goes simply like this. Summation from, let's say, just put summation to infinity, 1 over n to the p. P smaller equal than 1, divergence, p larger than 1, convergence. Done. This is one of those where you're going to use your eyes and look at the value. Just like your geometric. Remember geometric? You look at R and you know converge or diverge instantly. P series, same thing. You either know it or you don't, right? That's it. So when P is 1, well, it's a harmonic series, right? It diverges. If it's 1 divided by square root of n, hey, what's the power for square root? 1/2. So what's happening with that series? Diverges because it's less than 1. What happens if the power is 3/2? Converges because it's bigger than 1, right? 3/2 is 1.5. That's bigger than 1. So you will look at the value of P and immediately judge that. Now, I'm just going to point something out because issues. Summation of 1 over n squared versus summation of 1 over 2 to the n. Tell me, what am I trying to show with this? Yeah, they're different. So what's different? Yes?
N is showing which number is going to be squared in the other one, and the other one is showing what the power.
No, that's yeah, clear, but I'm talking about the tests.
Right, one is that geometric.
Yes. So huge difference, and right, both of these have 1, 2, and n, right? They're just in a different order. So one is divided by the polynomial, the other one is divided by the exponential. N squared and 2 to the n is not the same creature, and it's a different method, right? So now you have that, and this is the difference between the row 2 and row 4 on your sheet. Row 2 and row 4, right? Now we know that geometric is right, you look at R is 1/2, that one converges. Over here, P is 2, less than 2, right, converges. So that's, make sure you are clearly distinguishing between P series and geometric series. It's not the same creature. Okay, back to integral test. By the way, there's nothing interesting about P series. You either, P is bigger than 1 for convergence or smaller than 1 for divergence. And there is nothing else. And it only works when you have n to the power. Anything else added, subtracted from this immediately ruins the form, and it's no longer that test. So back to integral. So back to integral test. Let's take a look at more examples. Yes?
Is there a point where for P series or integral series, are there different situations where you have to use one or the other?
P series works only in this one case, where you have 1 over n squared or 1 over n to the p. If you have 1 over n squared plus 1, P series doesn't work anymore.
So then integral series works.
Then you would do the integral test, which becomes 1 over x squared plus 1. And we all know that's integral of 1 over 1 plus x squared.
1 over x squared plus 1?
Yeah. The inverse tangent, exactly. Boss. So if you have as this thing is going to take 15 minutes to start. Oh, there we go. So summation of 1 over n squared plus 1. It's not a p-series because it has this plus 1. So you would transform this into the integral test, do the 3 proofs, make sure it works, and then you would crank the integral test. It will go into arctangent, it would converge, and you would have your convergence. Okay? So that's the way this works. I mean, we could, let's do the example. Why not? Summation of, let's go summation of 3 divided by x squared plus 4 from 0 to infinity. Can we start at 0? Sure, because of plus 4, right? We can start at 0. It's okay. So now, if you're looking at this problem here, you can say, okay, the an, oh, not x, n squared plus 4. An is 3 over n squared plus 4. F of x is 3 over x squared plus 4 on the interval 0 to infinity. Is it continuous? Why? There is a simple answer. Yes?
Because the only x that gives you 0 on the bottom is -2.
Negative square negative 2 is going to become, it's 2i. You were thinking of 2i. Yes, because x squared plus 4 can never be 0. You can't make denominator 0. There is nothing you can do. I mean, you can cry, but it still won't work. So, is it continuous? Yes, it is. You cannot make denominator 0, and you're done. Is it decreasing? Well, you can do the derivative. So f prime of x of 3, and then you have the x squared plus 4 to the negative 1. No, that's f, sorry. So now we find f prime, which is negative 3 times x squared plus 4 to the negative 2 times 2x inside, which is f prime of x is going to be negative 6x divided by x squared plus 4, everything squared. Now remember that we are on 0 to infinity. So how do I know that this is decreasing? Well, derivative is always less than 0. What do I have? I have a negative number times always a positive number for x, because I can only pick positive numbers from here to plug in for x, divided by something that is squared. That's always positive. So all of that is equal to a negative number that's less than 0, and this means that the first derivative is always negative, which implies decrease on 0 to infinity, and that means check. So we have continuity check and decreasing check, time to make sure it's positive. Well, what's my f of x? My f of x is 1 over x squared plus 4. 3. Okay. So, what do I have? Denominator is always positive, right? X squared plus 4 is always positive. Obviously, 3 is always positive. And when you divide positive by another positive, you get a positive. There we go. So, yeah, check. So we proved continuous, decreasing, positive, which means that we can go and do the integral 0 to infinity of 3 over x squared plus 4 dx. Kick 3 outside, put the limit b goes to infinity, and get your integral of 1 over x squared plus 4 dx from 0 to b. And that is going to be 3 limit b goes to infinity. And now I have my inverse tangent. It's going to be 1/2 inverse tangent of x over 2. And that's because of the 4. In the formula, you have x squared plus a squared. Right? That's in the formula. And then you have 1 over a inverse tangent x over a. So if your a is a squared, and that's a 4, then a is 2. So you have 1/2 and x over 2. Inverse tangent computed from 0 to b. This is 3. Limit b goes to infinity. Oh, 3/2, sorry. Kick 3/2 outside. 3/2. And now you have your tangent inverse of b over 2 minus 0. And this is equal to 3 pi over 4. Because the inverse tangent at infinity is pi over 2. 3 pi times pi, 3 pi over 2, 3/2 times pi over 2 is 3 pi over 4. There we go. So it converges. And because it converges, we can write our answer. Since all 3 conditions hold, and integral 0 to infinity of dx over x squared plus 4, 3 in front, converges, the series summation 0 to infinity of 3 over x squared plus 4 converges by integral test. And we go on with our life to the next problem. Now for our next problem, we're going to pick something fun. So there might be a question, so how do I know that I am supposed to do the integral test? Well, one of the answers, obviously other than experience, is, well, you see something that you can integrate. And this next example is a perfect example for it. Summation of, they use k, we can use k. K goes from 3 to infinity. 1 divided by, lock the doors, k, ln k, ln of k. Right? You're dropping, huh? I quit. So an example. Guys, Thanksgiving is coming up. I mean, this example. Perfect. Haven't seen you in a year. What's new? Well, let's start with this one. I had this Calc2. I had this Calc2 class. It was brilliant. Now, looking at all possible tests we had so far, you start with divergence test on this one, and you have 1 divided by infinity of some sort. That's equal to 0, so that one is useless. It's not geometric, clearly, has ln's. It's not p-series, has ln's. And telescoping, well, telescoping needs that minus sign. Now you could go into partial fraction decomposition to make the final sign, but you can't do partial fraction decomposition because that's LNs. So by process of elimination, this is an integral test. But also you say, I need to integrate this. Oh, I have all of these ln k's, and then I have 1 over k for u sub. Easy. Right? Easy. Yeah.
U is over 3 is greater than e, so ln of k is going to be positive. Right.
Just.
Okay.
Good. E is about 2.7, right? So, perfect. Yep. Okay. So we have this, and we came up with we realized that we have to use integral test. So what's the AK? AK is 1 over k ln k ln of k, which means that f of x is 1 over x ln of x on 3 to infinity. So our first step over here is to convert our discrete problem into the continuous problem, and we are using 3 to infinity as our domain because the series goes from 3 to infinity. All we need to do is 3 proofs and we are done, right? Awesome. Is this continuous?
Yes.
Why? Is this continuous? Yes. Okay, good, sure, why not? Continue.
I think there's some theorem about continuous function.
Perfect. 2.6, Calc 1 2.6, continuity theorems. There are 2 theorems which you are supposed to know to survive these proofs. And guess what? Let's jump into available Calc 1 class. We can talk, let's go to the next one, Tuesday, Thursday. And we are going to go 2.6. This is the time for you to take some pictures or write some theorems down. First one is the following functions are globally continuous. Boom. Constant function, polynomial, exponential, logarithmic, sine, cosine, radical, and rational if denominator is not 0. All of these functions are globally continuous. That is a theorem, right? That is a theorem. So constant, polynomial, exponential, logarithmic, sine, cosine, radical, and rational. On their entire domain, make sure the rational function has no vertical asymptote, obviously, right? So x squared plus 1, x squared plus 4, we had some of those already. So ln is on that list. ln is under 4, right? ln x. So great. We have x times ln x. So x belongs here in number 2, and ln belongs in number 4. So each individual function that we have is continuous in that problem. We have 1 on top, which is constant function. The second theorem that you must know is this purple one. It appears as black, but it's purple. And it says function composition and function combinations are continuous. Function combinations, addition, subtraction, multiplication, division, squaring, and your composition, and that is ln of ln. Remember we had that one? Mm-hmm. So these are the 2 theorems that you guys need to prove any continuity over there. And obviously you are on restricted domain, so that helps because some asymptotes might creep in here and there, but they would happen maybe outside of the domain you care about, so you ignore them. Like 1 over x had the asymptote at 0, but we started at 1, so we didn't care. We deemed it continuous. So these are the 2 theorems that you must know, and those are the 2 theorems that you will call upon to solve these problems. Much better. So here we go. Is it continuous? Well, x and ln x are continuous on 3 to infinity. You are calling on the theorem of global continuity. Then we say function composition of continuous function gives a continuous function. So what I established here is that that's continuous, that's continuous, that's continuous, that's continuous, right? I established the continuity of all functions separate. And now the last is function combinations of continuous functions give continuous function provided that denominator is different than 0. And in our case, that's good because the bad points are 0, 1, and e, right? So none of those. Now in our case over here, we can just quickly say that 0, 1, and e are not elements of, I want to put this in the next, really? There we go. So here we go, we'll put it here. 0, 1, and e are not the elements of 3 to infinity. So f of x is continuous on 3 to infinity. So this is the continuity proof spelled out. You first establish continuity of each individual function, then you establish continuity of compositions and combinations, and then if you have the denominator, you deal with the denominator, making sure that none of the values that would make the problem explode are in the domain. Continuity check. Next one is, let's go positive because that's the cheap one. Positive. Why?
Because all values are going to come out positive.
Excellent. So yes, because x is element of, x is element of 3 to infinity. So all the input are positive numbers, and when you take a look at your function, you have you have a positive divided by the positive x, the positive ln, the positive of the positive, slash positive, it's always bigger than 0. So all of them are positive. Great. Check. Did not have to worry about that one. Decreasing. How's your triple product rule within the quotient order chain? Great. Stellar. I love that. So you can use the triple product rule, or we have another way of proving decrease. We can go back to our discrete domain, and remember for sequences, when we had the decreasing and non-increasing and increasing and non-decreasing and monotonic and all of those? Remember that there was a definition that it's decreasing if the an plus 1 is smaller than an. You can prove that. We can show decrease by proving an plus 1 smaller than an. Okay, we use the k's in this problem. Fine. ak plus 1 and then ak. We can show decrease by that. We don't have to go. All right, so let's go. Need to show that 1 divided by k plus 1, ln of k plus 1, ln of k plus 1 is smaller than 1 over k ln of k. That's what we need. Well, just cross multiply. When you cross multiply, we have k ln of k less than k plus 1 ln k plus 1 ln of k plus 1 and now what do I have? Do you see that factor by factor they are bigger? Can you compare k to the k plus 1? Do we see that k plus 1, which is bigger, is on the right side? ln is the increasing function. Do we see that you have the larger one again on the right? And this one here? Are we green? Yeah, we're green. It's decreasing. Because we just showed that each individual on the left is smaller than each individual on the right. So this holds. And when it holds, right, we're done. Great! We can integrate. So all we need to do is just to integrate 3 to infinity dx over x ln x ln of ln x, and that's it. Now this is a Calc 1 question. A little bit more advanced than Calc 1 question, but still Calc 1 question. U sub. Exactly. Basic U sub. U equals ln x. What's the U?
I think U can be ln x.
Yeah. It can. And I'm very happy that you saw it. But we have more. It could be ln of x, because in that case, yes, use the chain rule and it will be one move. But we'll do it in steps. So limit x goes to infinity, no x, b, 3 to b, and now this is my du. So I have du over u ln u. Now what? G substitution. G is what? ln u. So what's dg? 1 over u du. That's the dg. So now we have the limit. B goes to infinity. We're not going to change these limits. We'll go back. So we have dg over g. And what's that integral? ln, exactly. ln of g, absolute g, which is ln of u. which is also?
So that's ln of ln.
That's ln of ln of x. Excellent. Now we're talking. Computed from 3 to b. B goes to infinity. All this work just for this to explode. Since all three conditions hold and integral of f of x, I don't want to write the whole thing, dx diverges series summation of, oh, I gotta write it now, k ln of ln k diverges by the integral test.
Can't write series B and K. Or B and K.
Yeah, AK, but stay there. Gotta box you. Cool, huh? I know. Here's one for you to enjoy on your own. Summation 1 to infinity ne negative n squared. At least continuity is easy. take a look. So I know it's integral test because I can see u substitution immediately, right? So we can see u sub, and that immediately says, let's try. Not every problem, obviously, is going to work out, but because of the proofs, but, you know. So is it continuous? Positive, and yes, because x is on 1 to infinity, and e to f of x always gives positive values. So positive times positive equals positive. We're good to go. And the last one over here is decreasing. So this one could fail, and then you can't use integral test, right? Such is life. Let's see. So for the decreasing, we have f of x equals x e to the negative x squared. So you can do the product rule with the chain and all of that stuff, or maybe it will be better, faster, easier to use the discrete, where you take a look at k and k plus 1. Right, so we're doing the derivative here because it's just a product rule, so it's not a big deal. F prime of x is copy the first, derivative of the second, plus copy the second, derivative of the first. And f prime of x, we factor out e to the negative x squared, and what's left in parentheses is 1 minus 2x squared. Now remember that x is bigger than 1, right? It's called the blue screen of death. Oh, it's not coming back. Go. Yep, it's telling us to go home.
Record the screen with the camera. Record the screen with the camera. It'll look like a bad bootleg movie.
Hold up the tablet.
So as you can see, it's decreasing, and now we integrate. I have to restart the projector because it's so you have your derivative. I'm not sure if you wrote the derivative, but the derivative will always be negative because of that second term, which was 1 minus 2x squared, yes. So that term is always negative times e term, which is always positive. Positive times negative is always negative. And we have that the function is always decreasing. And all you need to do now is the type 1 improper integral with the basic u because it is set up for u sub. Okay, yeah, here we go. It's not going to take long. So you can do the integral, right, with the u sub, and then you should get convergent at the end. when you get the convergent, that means that the series is convergent. You write your answer, and you're done. Perfect. So far, we know all three conditions hold, and all I need to do now is the integral. Integral 0 to infinity? Or 1 to infinity? 1 to infinity of x e to the negative x squared dx. We use u sub as negative x squared, and then the du is negative 2x dx. I need this negative everywhere, so negative limit b goes to infinity, integral 1 to b, and then this is e to the u du, negative limit b goes to infinity of the, oops, I don't need integral. Integral of e to the u is e to the u, so e to the negative x squared from 1 to b.
Still a one half.
Yeah, there's 1/2.
Because it's negative 2x and we only have an x. So you have to.
For the sake of mathematical correctness, I will put the negative 1/2 in front. It's completely irrelevant in the end because we don't care about the numerical answer. We just want to know if it's finite number or infinity. So if you get 3 times a half is 3 halves, but we don't actually care if it's 3 or 3 halves. We just care that it's a finite value. But
In the exam, if we don't write, do we get?
I probably won't even see it.
Oh, okay.
You're just looking for if we got the answer.
I first look at the answer and then I my way back. It cuts 5 hours of grading down into 3.5. It's efficient to look at your answers on the exam backwards rather than forward. So I might completely miss that you missed your 1/2. So what do I have? I have limit b goes to infinity of e to the negative b squared minus 1 over e. This is gonna go to 0. It's convergent. I don't even care what the values are. It's just there's no infinity anywhere, so I'm done. Answer, since convergent. And here's the box for your answer. It's the same answer like always. Yes?
If you say it's convergent by integral series instead of by integral test, would that be wrong?
It's convergent by integral series test. Integral series test is the full name of the test.
If you accidentally just say series or just say test, would you get points off?
No, you should, but no.
Okay.
I mean, do you want the? Okay, I'll put a note to make sure you take off for. So that's the divergence integral and p series. Bye.